Hi, my name is Ray, and this is my Physics 6C pencast for problem 26 from homework number 2. This question has two parts, and it starts with a positive 12 NC charge located at the origin. Part A asks us, what are the electric fields at the position for X and Y when they are positive 5 centimeters, 0 centimeters, negative 5 centimeters, and positive 5 centimeters, and negative 5 centimeters, and negative 5 centimeters, telling us to write each electric field vector in component form. The second part of the question is to draw a field diagram showing the electric field vectors at these 3 points. So, to start this question, we will draw the field diagram so that we have an idea of what it looks like. First, I will draw the X and Y axis. And so, the origin, which is here, contains the positive 12 NC charge. The first position, which is positive 5 centimeters and 0 centimeters, will be labeled as the first electric field. And the direction is positively towards the x-axis. And the second will be here, which is the negative 5 centimeters and positive 5 centimeters. And this is the direction of the electric field vector, or the second one. And then the third one is here, which is negative 5 centimeters and negative 5 centimeters. We can see the distance for the second and third are here at negative 5, while the second and the third have positive and negative respectively. And so this is our field diagram, which answers question B. And after we solve question A, I will label the values of each electric field. So for part A, we are given a charge at the origin. So the charge is positive 12 NC, which is also equal to 1.2 times 10 to the negative 8th C. And so, electric field values, the equation we will use is E, or electric field, is equal to the Coulomb's constant times the charge over the distance squared. Coulomb's constant is equal to 9.0 times 10 to the 9th newtons times meters squared over Coulomb squared. So with the three electric fields, we need their three distances, while the charge will be the same. So for the first distance, R1, it will be equal to 5 centimeters, which is also equal to 0.05 meters. And then the second distance is equal to this, which can be found by adding the squares of the x and y component distances and then square rooting it using a formula we've all used many times. So the first is negative 5 centimeters squared plus positive 5 centimeters squared. And that gives us the square of 25 centimeters squared plus 25 centimeters squared, which is equal to the square root of 50 centimeters squared. Meaning that R2 will be equal to 7.071 centimeters, which is also equal to 0.07071 meters. And here you can see that although for the distance of electric field 3, the sign on the y is different, it will still lead to the same result, being that it is the square root of negative 5.0 centimeters squared plus negative 5.0 centimeters squared, equaling 7.071 centimeters or 0.07071 meters. Now, to find the value of the first electric field, we will use the Coulomb's constant multiplied by the charge over the distance of the point and the origin, which we found earlier, squared, which gives us 9.0 times 10 to the 9th newtons times meters squared over coulomb squared. That multiplied by the charge, which is 1.2 times 10 to the negative 8th coulombs, all over the distance squared, which is 0.05 meters. Here we see that one of the c's cancel with another, and the meters, which will be squared, cancel with each other. So we'll move the square next here so we remember it. And based on this, our final unit will be newtons over coulombs. After entering these numbers into a calculator, I find that the value of the electric field at that position is equal to 4.32 times 10 to the 4th. And here we will write the units, which are newtons over coulombs. Now we need to write the electric field vector in the component form. And since the direction of this is positively in the x direction, we will write 4.32 times 10 to the 4th newtons over coulombs with I hat. So we have found the first electric field vector. Oh, my bad. And so the second one, the value is equal to the Coulomb's constant times the charge over the distance squared. And this distance is different because we found it earlier. From the origin to the second point, the electric field vector has a slightly longer distance. And so we will write the Coulomb's constant, 9 times 10 to the 9th newtons times meters squared over coulomb squared, multiplied by the charge of 1.2 times 10 to the negative 8th c, all over the distance squared, which is 0.07071 meters squared. And once again, we can cancel out all the units just to leave us with newtons over coulombs. And so after entering it into a calculator, I got 2.16 times 10 to the fourth. Now, to put the second electric field vector into components form, it will be equal to. So first we see the value in the x direction. It will be negative at a degree of 45. So we have a negative value multiplied by the cosine of 45. And we add that to the positive. Since the y direction is positive, it will equal to the value multiplied by sine of 45. And that will give us negative 2.16 times 10 to the fourth. Oh, I'm sorry, this was newtons over coulombs as well, which is here as well, multiplied by 1 over root 2 in the I with I hat. The negative indicates that this goes in the negative x direction. Add that to 2.16 times 10 to the fourth over n over c, multiplied by 1 over root 2 as well, because sine of 45 and cosine of 45 are equal to 1 over root 2. Calculating this, I also used the calculator, which gave me negative 1.527 times 10 to the fourth I hat plus, which was the same but a positive 1.527 times 10 to the fourth. And the j, which I forgot earlier, indicates that it's the y direction, and the positive is showing that it goes in a positive y direction. So here we have our electric field vector for the second position in component form. Now moving on to the third. Find the value. First, we do the same. It's equal to the Coulomb's constant times the charge over the distance to the third position squared. That is equal to 9.0 times 10 to the ninth newtons multiplied by meters squared over coulomb squared. The charge is still 1.2 times 10 to the negative 8th c. And since, even though the direction is different, the distance is the same, so we still get 0.07071 meters squared. Now, if you look, these are the same, meaning our answer for the value is the same, which is 2.16 times 10 to the fourth newtons over coulombs. Now to find the electric field vector in component form, it will be different, because here we see it goes in the negative x direction as well as the negative y direction. So we have negative times cosine 45 plus negative sine of 45. As we previously saw, 2.16 times 10 to the negative 4 multiplied by 1 over root 2 gives us 1.527 times 10 to the fourth. So, negative 2.16 times 10 to the fourth multiplied by 1 over root 2 I hat, showing us the x, minus 2.16 times 10 to the negative fourth 10 to the fourth, sorry, multiplied by 1 over root 2, the j, will be equal to negative 1.527 times 10 to the fourth newtons and coulombs, which I forgot earlier, in I hat, proving that it's the x direction, subtracted by 1.527 times 10 to the fourth newtons over coulombs, j hat. So now we have found the values of the electric field vectors in component form for the third position, the second position, as well as the first position. And to finish the problem, I will label them on the field diagram. So we see E1 is equal to 4.32 times 10 to the fourth newtons over coulombs I hat, which is, so the charge to the position, the electric field vector is positive on the x-axis. And then for this second one, it is equal to negative 1, I'm sorry, I boxed the wrong answer for the second one. Please disregard. And so I will go back again and box the correct answer. So the electric field vector in component form for the second position is equal to 1.527 times 10 to the fourth newtons over coulombs I hat, plus, because it is a positive on the y-axis, 1.527 times 10 to the fourth newtons over coulomb j hat. And now the final one with the third position, the electric field vector in component form is equal to negative 1.527 times 10 to the fourth newtons over coulombs I hat, subtracted by, showing that it's a negative direction for both the x and y, 1.527 times 10 to the fourth newtons over coulomb j hat. And that completes this problem. Thank you for watching.